Welcome to today's paper reading. Today's paper is titled C2C, Component to Composition Learning for Zero-Shot Compositional Action Recognition. This paper was published on AR14 by Rongchang and colleagues from Jiangnan University and the University of Surrey. The abstract introduces the concept of compositional actions, which involve dynamic elements like verbs and static elements like objects. Humans can recognize these compositions easily, but machines require a model with compositional generalization ability. To address this, the authors propose a new task called Zero-Shot Compositional Action Recognition, Sth-com. They introduce a new benchmark, something composition, Sth-com, based on the something v2 dataset, and a novel learning method called component to composition, C2C. The experimental results show that the proposed framework significantly outperforms existing methods and sets a new state of the art. The benchmark and code are made available for further research. The Zero-Shot Compositional Action Recognition (ZSCAR) task involves recognizing actions that are composed of verbs and objects that have been seen before, even if the specific action itself has not been encountered. This task presents significant challenges in video understanding, requiring the comprehension of both dynamic and static components, and the ability to generalize to novel compositions. To address these challenges, the authors propose the component to composition, C2C method, which independently learns the dynamic and static components and then uses a consensus approach to recognize actions. Additionally, a new dataset, something composition, Sth-com, has been created to facilitate the training and evaluation of the C2C method, demonstrating its effectiveness in achieving state-of-the-art results. Figure 1 illustrates the Zero-Shot Compositional Action Recognition (ZSCAR) task, which challenges models to recognize actions they have not encountered before. These unseen actions are composed of verbs and objects that the model has seen in previously observed actions. The task requires understanding both dynamic, verbs, and static, objects, components, and generalizing this understanding to new, unseen combinations. This capability is crucial for developing applications in autonomous vehicles and robotics, where recognizing novel action compositions is essential for effective operation in open scenarios. Figure 2 illustrates the component to composition, C2C, learning framework, which is designed to address the Zero-Shot Compositional Action Recognition (ZSCAR) task. The framework consists of two main modules, the Independent Component Learning Module and the Component to Composition Module. In the Independent Component Learning Module, verb and object prototypes are aligned with corresponding visual features to obtain component scores. The Component to Composition Module then infers actions through two paths, dynamics and static. In the dynamics path, verb prototypes and visual features are used to compute conditional object scores, which are then multiplied with independent verb scores to obtain action scores. The static path follows a similar procedure. The final output is a consensus of the results from both paths, ensuring a comprehensive understanding of the action compositions. In video action recognition, previous methods have primarily focused on using 2D CNNs with separate temporal operations, 3D CNNs to extract spatio-temporal features, and more recently, transformer-based models. Zero-shot action recognition aims to recognize actions not seen during training by mapping video features and action embeddings into a common semantic space. Compositional action recognition, on the other hand, focuses on the compositional nature of actions, decomposing them into spatio-temporal scene graphs and recognizing verb-object compositions. The Zero-Shot Compositional Action Recognition (ZSCAR) task is defined as recognizing actions composed of verb-object pairs that have not been seen during training. This task requires a model to generalize beyond the training data, recognizing combinations of verbs and objects that were not explicitly paired in the training set. The training set, denoted as train, consists of video samples labeled with actions from a subset of verb-object pairs. The validation and test sets, val and test, include both seen and unseen action categories, following the generalized zero-shot learning setting. Table 1 provides a detailed overview of the statistics for the something composition, Sth-com, benchmark. The table highlights the number of objects, verbs, and verb-object actions across the training, validation, and test sets. Specifically, it shows that there are 248 unique objects and 161 unique verbs, resulting in a total of 5,124 verb-object actions. The dataset is divided into training, validation, and test sets, each containing a specific number of samples, with a total of 79,465 video samples. This table is crucial for understanding the composition and scale of the Sth-com dataset, which is essential for evaluating the performance of models in the zero-shot compositional action recognition (ZSCAR) task. The component-to-composition (C2C) learning framework is designed to simulate the process of human assembly to infer compositions. It starts by analyzing the compatibility of various components to propose reasonable compositions. This framework includes two main modules: independent component learning and component-to-composition learning. Additionally, an enhanced training strategy is devised to better generalize to unseen actions. Key challenges addressed by this framework include component domain variation and the need for balanced learning between seen and unseen actions. Figure 3 illustrates the challenge of component domain variations in unseen actions. On the left, it shows how an object like book can exhibit notable differences in appearance between actions like close a book and bend a book. On the right, it depicts the strategy to address this issue by reducing spurious information and increasing the independence between component-specific features. This approach helps the model to better handle the variations and dependencies that may confuse it when encountering new action categories. Figure 4 illustrates the variations in component compatibility between the training and test sets. On the left, it shows that the component relations differ significantly between these sets. To address this issue on the right, the figure demonstrates the use of observed conditional scores to fit the seen relations and encourages the model to imagine unseen actions. This approach helps avoid the model being limited to only seen relations. The method involves calculating observed conditional probabilities in the training set as observed conditional scores and using cut-mix to assemble samples for imagined unseen actions, thereby balancing the learning of both seen and unseen connections. Table 2 presents a comprehensive comparison of the component-to-composition learning (C2C) method with state-of-the-art (SOTA) methods on the Sth-com dataset. The comparison is conducted using the vision model with word embedding model paradigm. The table reports performance metrics for both the vanilla version of C2C, which only uses Sth-com and Comp, and the enhanced version, which employs the advocated enhanced training strategy. Notably, the enhanced version of C2C demonstrates superior performance across various metrics such as verb and object seen and unseen accuracies, HM, harmonic mean, and AUC, area under the curve. The video Swinty model, which is adapted from the transformer architecture, shows particularly high HM and AUC scores. Since the AD method is specifically designed for transformer architectures, it is only adapted to VideoSwin in this comparison. This table highlights the effectiveness of the enhanced C2C training strategy and the performance capabilities of the VideoSwinty model and component-to-composition learning tasks. Table 3 provides a detailed comparison of the current state-of-the-art, SOTA, clip-based methods on the Sth-com dataset. The table highlights the performance of various methods in terms of verb and object accuracy, as well as their scores on seen and unseen actions. Additionally, it includes metrics such as HM, harmonic mean, and AUC, area under curve, to evaluate the overall effectiveness of these methods. This comparison is crucial for understanding the strengths and weaknesses of different approaches in handling compositional generalization tasks. The evaluation metrics used in this study include the accuracy of verbs and objects, denoted as verb and object respectively. Additional metrics such as seen, unseen, harmonic mean, HM, and AUC are derived by adjusting the scores of seen actions with a constant ranging from negative to positive infinity. This adjustment shifts the model's bias from unseen to seen actions, producing a seen-unseen curve. The implementation details involve setting the coefficients alpha, beta, and gamma to 0.2, 0.1, and 0.1 respectively, and a cut-mix probability p of 0.7. Comparisons with state-of-the-art methods show significant performance gains by adapting existing compositional zero-shot learning methods to the proposed Sth-com dataset and comparing on the CGQE dataset. Figure 5 illustrates the seen-unseen action accuracy curve, which is generated by progressively biasing the model from unseen to seen actions. The curve intersects with the x-axis at the best accuracy of seen actions and with the y-axis at the best accuracy of unseen actions. The harmonic mean, HM, is calculated as 2, seen * unseen, / seen plus unseen, and the area under the curve, AUC, represents the overall performance. This figure helps in understanding the model's ability to balance between recognizing seen and unseen actions. Figure 6 illustrates the top 3 compatible components for various samples, maintaining one component constant. For instance, when the verb is squeeze, the compatible objects for the first sample are cloth and paper, which are visually relevant and compatible with squeeze. In the second sample, the model identifies different objects, where the basket, though not visually present, is compatible with squeeze, and the bed, though visually close, is not combinable with squeeze. This demonstrates the model's capability to assess component compatibility based on both visual content and component attributes. Figure 7 presents examples of both successful and failed predictions made by our methods. In the top row, the model accurately predicts the given actions, with the second and third predictions closely related to the visual content, such as fold paper for the first sample and tear paper just a little bit for the second sample. The bottom row illustrates some failures, where the predictions, though incorrect, still reflect the video content, like move part of plant and tear leaf into 2 pieces for the second example. These failures highlight the limitations of the proposed method, particularly in distinguishing objects or verbs with similar visual appearances. Table 4 presents a comprehensive comparison of the proposed C2C method with state-of-the-art, SOTA, methods on the CGQE dataset. The table highlights the performance metrics of multiple seen, unseen, harmonic mean, HM, and area under the curve, AUC, for each method. Notably, C2C demonstrates superior performance across all metrics, achieving the highest HM and AUC scores. This indicates that C2C not only excels in recognizing seen categories but also significantly improves the recognition of unseen categories, which is crucial for zero-shot compositional action recognition tasks. Table 5 presents the results of various hypotheses attempting to infer compositions from components. The table categorizes these hypotheses into different types, such as compos, knowledge agnostic, and dynamic-centered, and provides numerical results for each. For instance, the compos hypothesis yields a score of 35.1, while the knowledge agnostic hypothesis shows scores of 48.4, 43.1, 38.7, and 36.8 across different metrics. The dynamic-centered hypothesis scores 36.7. These results offer insights into the effectiveness of each hypothesis in inferring compositions from components. Table 6 evaluates the effectiveness of various elements in an enhanced training strategy. The table lists components such as Th-com, comp, lind, cutmix, con, and ln, along with their impact on metrics like HM and AUC. The data shows incremental improvements in performance as more elements are incorporated into the training strategy, indicating their individual and combined contributions to the overall effectiveness of the strategy. Table 7 presents the accuracy percentages for methods applied to actions containing verbs that cause deformations. The vanilla method achieves an accuracy of 70.1%, while the vanilla plus lind method shows an improvement with an accuracy of 71.8%. Additionally, the verb composition method records an accuracy of 60.2%. These figures highlight the effectiveness of different methods in handling actions characterized by verb-induced deformations. Table 8 presents the unbiased accuracy percentages of seen and unseen actions, along with their corresponding harmonic means, HM. The baseline method shows an accuracy of 36.8% for seen actions and 17.2% for unseen actions, with a harmonic mean of 23.5%. The table details the impact of various enhancements, such as adding Lcon, cutmix, and Lne on these metrics. Notably, the integration of Lne and Lcon results in the highest harmonic mean of 24.9%, indicating a significant improvement in balancing the accuracy of seen and unseen actions. This paper introduces a new task called Zero-Shot Compositional Action Recognition, ZSCR, which focuses on compositional generalization within the video modality. Along with this task, a benchmarking dataset named Sth-com and a baseline method called C2C are proposed. An enhanced training strategy is also presented to tackle two main challenges in ZSCR: component domain variations and component compatibility variations. The approach shows better performance than existing compositional generalization solutions in both image and video-based zero-shot compositional learning settings. Positive and failure cases are highlighted to demonstrate the effectiveness of the proposed methods. This research is supported by several key funding sources: the National Key Research and Development Program of China, the National Natural Science Foundation of China, and the 111 Project of the Ministry of Education of China have all provided crucial financial backing. Specific grants include 2023 YFF 1105102, 62020106012, and B12018. Additionally, international support has been received from the UK EPSRC, with grants such as EP/V002856/1 and EP/T022205/1. Thank you for watching.